Hello everyone. We're going to look at one of the last problems in basic vector mechanics. In this particular problem, we will be given a force vector. We will be given the magnitude of the force vector, and we will also be able to find out a couple of points on its line of action. And then we want to take this force vector and we want to project it on some arbitrary direction. And along that arbitrary direction, we want to find the projection vector of this force vector. And we would also like to find the vector that is perpendicular to the projection vector. All the details will be described by means of the following figure here. First of all, I'll set up the Cartesian coordinate frame in 3D. So I have the positive z direction, I have the positive x direction, and then I have the positive y direction. Alright, so this is positive x, positive y, and then positive z. And now I have an L-shaped pipe which is set up along the zy plane as shown. So I'm going to mark off a point which we will call as some point C right here. Then I'm going to draw a line that is parallel to the y direction, and I'm going to bring this line down by a little bit. Alright, as you will see here, and I'm going to construct this in 3D just to give it some kind of a geometric shape. This is some kind of a pipe element which is held here. I'm going to shade this in a different color. So this is let's say, for example, an L-shaped pipe, and this L-shaped pipe is probably fixed at the point C, and just to give it a little bit more of a support, we're going to have a cable that is going to run from, let's call this point here as the point A, and let's call this as the point B. Let me call the origin here as the point O, and there is a cable that's going to be running from the point A to the point O. So here is that particular cable drawn in red color. And cables, as we have discussed in lecture, they are always in a state of tension, which means that there is a certain force acting along the cable directed from point A to point O, and this force is going to be marked here. So the force along the cable is given by a magnitude of 100 newtons. So this force here, F, is 100 newtons. And we also need some dimensions as to where the points are located. So I'm going to drop a line from the point A. This is going to intersect the y-axis right here, because the line BC is parallel to the y-axis. Now here are the dimensions that I'm going to be thinking about. So the first dimension is right here. This is the height of the point C above the xy plane. So this height, let's call this as 6 meters. Then I'm going to have the point A, which is situated right there. I need to know its distance along the y-axis, so I'm going to draw a line that is parallel to the y-axis. I'm going to join this here, and this dimension is given to us as 8 meters. And then the point A is situated at a height of 3 meters from the xy plane. Alright, so this height here is going to be 3 meters. And key points here are the line BC is parallel to the y-axis. So BC is parallel to y-axis. The line from B to A is parallel to the z-axis here. So I'm going to write that here. So BA is parallel to the z-axis. And these are the dimensions that are given to us. We have the force vector F. There are a couple of things that we need to find out in this particular problem, and what are these things? First of all, the main thing to find out here is I want to find the projection of this force F along a line joining the point C and the point A. Okay, so find the projection of the force vector F along a line joining the point C and the point A. Alright, so this is the first part of the problem. And the second part of the problem is find the vector that is perpendicular to this projection vector and lying in the same plane as the projection vector. Okay, so find the vector that is perpendicular to projection of the vector f along line from C to A. And it is quite obvious that all of these have to be expressed in terms of Cartesian vectors, and eventually we will also find out the unit vector along the vector that is perpendicular to the projection of f drawn from the line C to A. Alright, so these are the things we need to find out. Just to rehash the problem once again, I have some kind of an L-shaped contraption here. This is a pipe. This is probably fixed at the point C or hinged at the point C. And then I have a cable which is running from the point A to the point O. This is holding this guy in place. We are not really worried about how this is being held in place. All we are worried about is that since this is a cable, right, so this red guy here is the cable. Since that is a cable, we know that cables are always in a state of tension, and so that tension is given as 100 newtons directed from the point A to the point O. What do we need to find out? We need to find the projection of this force along a line joining the point C and the point A. So here is a line that is joining the point C and the point A, more or less a straight line. We need to find the projection of this force along that particular line, and then what do we finally need to find out? We need to find out the vector that is perpendicular to the projection of this force along that particular line. Alright, so I'm going to restate the problem by looking at the figure once again and gleaning whatever is the necessary information from the figure. So the first thing we need to do is we need to see, okay, where is the projection vector in terms of a basic figure, and then where is the perpendicular vector to the projection vector. Alright, so once again my typical coordinate system x, y and z. So this is z, this is x, and this is the positive y-axis. And then I have this line from the point C to the point B, and then from the point B to the point A, this L-shaped line, as I'm going to draw here, parallel to the y direction, and then this comes down a little bit. So this is the point C, this is the point B, which is not very important to us right now, and then I have the point A. I have a line joining the point A and the origin, which we drew in red before, so I'm just going to redraw that once again in red. And then I'm going to look at a line which is joining the point C and the point A. This is going to be drawn in the blue color, as you will see here. Then I have a force vector which is pointing from the point A to the point O. So O is the origin of the coordinate system. So I have this force vector here. Let me assume that the tail of this force vector is starting at the point A, and this force vector has a certain magnitude, and this is having a magnitude of 100 newtons. Now what do I need to find? I need to find the projection of this force vector along this particular line here, which means that if I take a line from the head of the force vector F and I drop a perpendicular onto the line from C to A or A to C, then I get the projection vector. So notice this here. So I take a line from the head here, and then I see that this is a 90-degree angle, and there you see I have my projection vector. So this guy here is going to be F projection. And then what is the vector perpendicular to the projection vector lying on the same plane as the projection vector? Is this little creature here, and so this I'm going to call as F perpendicular. Alright, and I have a nice triangle here which I'm going to shade in blue. And the important thing is I'm no longer worried about what is happening in the rest of the problem. All I'm looking at are the lines joining point O and point A to the point C and point A. And before I look at these lines in slightly better view, I'm going to look at the coordinates of point C and point A and so on. And we already have all that information. This is at a height of 3 meters right there. And then it is at a distance of 8 meters, I'm sorry, 4 meters, and this is at a height of 6 meters along the Z direction here. This is the point C, so this is 6 meters right there, and then of course this is the origin O. So if I write out the coordinates of points O, point A and point C, then that's pretty much what I need to look at in terms of how to find the position vectors and so on and so forth. Before that, there is something more important that I need to do. I'm going to look at the line AC, I'm going to look at the line OA, and then I'm going to look at that triangle there. Alright, so here are the lines. So line from A to C, drawn in blue, and then I have the line from O to A, which is drawn in red. I'm going to look at that little triangle that we constructed in blue. I'm going to draw it slightly bigger, just so that we have more space to write things out. So this is the point A, this is the point C, this is the point O. Alright, and then I have this perpendicular which is dropped here. So I complete the triangle. This is now my F projection. This is a 90-degree triangle right there. This is the vector F, which has a magnitude of 100 newtons, and then this creature here is F perpendicular, and I'm going to call this angle here as the angle theta. Alright, so that's a right angle triangle. That is something important to realize. And just to say that these are the same triangles, I'm going to shade them in. Okay. So we have all this information right now. I'm going to write out the coordinates of the point A, the point C and the point O, because these are my points of interest. Point O is really easy because it's at the origin, it's 0, 0, 0. So many meters. Then I look at the coordinates of point A. Look at the point A. The point A is on the ZY plane. It's at a distance of 4 meters along the Y axis. It's at a distance of 3 meters along the Z axis. So this is going to be 0, positive 4 and positive 3 meters. Look at the point C. The point C is a point on the Z axis, which means that it's at a location of 0 meters along the X, 0 meters along the Y, and scooting up by 6 meters. Alright, so this is going to be 0, 0 and 6 meters. Alright, so I have these points of interest for me, and now the thing that I need to look at are the following. You notice that the direction of the projection vector is going to be from the tail of this force vector to the point where the perpendicular is intersecting the line AC, which means that the unit vector along the projection vector should be the same as the unit vector from A to C. Right, so I'm going to call that unit vector as UAC, and then I'm going to have another unit vector, which is the unit vector along the line of action of the force F. What is that going to be? That is going to be the same as the unit vector from the point A to the point O. It is very important that we label it in the right direction. So this is going to be from UA to O. Alright, and we are going to look at this figure once again. I'm going to redraw this figure once again, much to I guess everybody's consternation, but this cannot be helped. So here is the picture redrawn once again. I have point A and C shown in blue, then I have the point O and the point A shown in red, and then I have the force vector there. Right, so this is the force vector. Then I drop a perpendicular and I get the projection vectors and I get the perpendicular vector. So this is going to be F projection, then this is going to be F perpendicular, This is a 90-degree triangle. This angle here is theta, and then this is the force vector F, whose magnitude is 100 newtons. Here is the point A, here is the point O, and here is the point C. Alright, and we also have information on the coordinates of A, O, and C. Just to rewrite that once again, so 0, 0, and 0 meters. Point A from the previous page was 0, 4, and 3 meters, and point C, a point on the z-axis, was at a height of 6 meters along the positive z. Now unit vector along the line from A to O, this is not UOA, this is UAO, and that is really important to understand. Right, so this unit vector is UAO. What is the unit vector along this line from C to A? The direction of the projection vector. Look at the direction of the projection vector. This is pointing in this direction here, which means that that is going to be UAC. And then I have the perpendicular vector, the vector perpendicular to the projection vector. I'm going to call the unit vector along its line of action, which I'm going to mark out here, and I'm going to call it as U perpendicular. Alright, so we will write out all this information in terms of how to express the force as a Cartesian vector. First of all, I'm going to write the force F as a Cartesian vector. Okay, so the force F is going to be the magnitude times the unit vector along its line of action. This is going to be the magnitude times the unit vector along the line of action is UAO. Unit vector is nothing but the position vector divided by the magnitude of the position vector. Then I'm going to write the same thing for the projection vector. F projection is going to be magnitude times its unit vector. This is going to be the magnitude of the projection vector times its unit vector. What is its unit vector? It is UAC. And so this is going to be F projection times R AC by magnitude of R AC. And then the last creature is F perpendicular. It's going to be the magnitude times U perpendicular. Now we have no information on U perpendicular because I don't know what the point on this line here are. I don't know what these points are, so this is something we don't know yet, so we do not have the luxury of writing out U perpendicular in some of these forms as you have seen here. But the key fact, which I'm going to write here, so the key is that we have a right angle triangle, or we basically have a triangle which is formed by three vectors. I have the vector F, I have the vector F projection, I have the vector F perpendicular. They have to follow the triangle law of addition of vectors, which means that the vector F is F projection plus the vector F perpendicular. So this is the triangle law of addition. So these are the vectors. If you want to write them as vectors, you are welcome to do that here, but they have to obey the law of addition. Alright. So using information from the previous page, we are going to write out the force vector F first. So we have the force vector F is the magnitude times its unit vector, which we found out was UAO, or magnitude times RAO by the magnitude of RAO. And I know the coordinates of O, I know the coordinates of A. The coordinates of O, 0, 0 and 0. Coordinates of A were 0, 4 and 3 meters, which means that if I write out the force vector, F is going to be the magnitude, which is 100 newtons, times the position vector from A to O, which means coordinates of the last point, which is O, minus the coordinates of the first point, which is A. So this is going to be 0 minus 0, so that's 0I. Then I'm going to have 0 minus 4, so this is going to be minus 4J. And then I'm going to have 0 minus 3, which is going to be minus 3K. divided by the square root of the sum of the squares of the components of the position vector. So that's 0 square, 4 square and 3 square. 4 square and 3 square is 16 plus 9 is 25. Square root of 25 is 5. Then upon simplification, I now have the force vector F as follows. So this is going to be 0I minus 80J minus 60K so many newtons. Alright, and I also have the unit vector along UAO, which we wrote in this particular form. This is 0I minus 4J minus 3K divided by 5. Alright, so these are two of the useful pieces of information that we have. I'm going to sneak in the coordinates of the point C right here. Is 0, 0 and 6 meters. And so I can now write the unit vector along the line joining C and A. So this is going to be UAC is the position vector by the magnitude of the position vector. Position vector from A to C. Coordinates of the last point minus the coordinates of the first point. So this is going to be 0 minus 0. So that's going to be 0I. Then I'm going to have 0 minus 4. So that's a minus 4J. I'm going to have a 6 minus a 3. That's a plus 3K. Divided by the square root of the sum of the squares of the components. So that's 4 square and 3 square, which 16 and 9 is 25. Square root of 25 is 5. Alright, so I have the force vector, I have the unit vector along AO, I have the unit vector along AC. Now we need to look at how to find out the projection vectors and how to find the vector perpendicular to the projection vector. Alright, and I'm going to look at the triangle once again. You can either draw it from scratch, or I'm going to draw it from scratch very quickly. I have all these vectors here and one more guy here. So this is F, this is F projection 90 degrees, and F perpendicular, A, O and C. We will call this angle as theta, and then I know this unit vector is UAO and this unit vector is UAC, and then the unit vector along the perpendicular is U perpendicular. Alright, now how do I find out the angle theta? If I can find out the angle theta, then pretty much my problem is done, right? Because then I can say that F projection is F times cosine theta, and then F perpendicular is F times sine theta, and I can make use of the triangle of addition or subtraction in order to find out F perpendicular or F projection as a vector. And so to find out the angle theta, we have gone through this in class. If I know the unit vector along this line and I know the unit vector along that line, the dot product of those two unit vectors is going to give me the angle theta. Alright, so I have cos theta as UAO dotted with UAC. Dot product is commutative, which means it makes no difference whether you do this versus that and that versus this. And so if I write this out, UAO from the previous page was 0I minus 4J minus 3K divided by 5, dotted with UAC was a similar minus 4J but at 3K divided by 5. And so this implies cos theta, if I do the dot product, this is going to be 0 times 0, so that's 0, and then I'm going to have a minus 4 times a minus 4, and I'm going to have a minus 3 times a plus 3. All of this will be divided by 5 times 5. Minus 4 times minus 4 is 16, and then this is minus 3 times plus 3 is minus 9. So I have a 16 minus 9 divided by 25, and so cos theta, after doing all this calculation, is going to give me 0.28, which means theta is cos inverse of 0.28, or theta upon solving is going to give me 73.7 or approximately 74 degrees. right? So I'm going to get theta to be 74 degrees approximately, based upon the dot product that we have done here. And once I have theta, then the rest of it is fairly straightforward. Let's look at that now. Now, for the purpose of simplicity, I'm just going to draw only the triangle without worrying about the rest of it. So I have the force vector F, then I have the perpendicular vector, and then I have the projection vector. So this was F, which was 100 newtons. This was theta, F projection, and then F perpendicular, 90 degree angle. I found out theta was cos inverse of 0.28, which was approximately 74 degrees. And so I can find out the magnitude of the projection vector. This is going to be F times cosine theta, or 100 times 0.28 or 28 newtons. F perpendicular is going to be F times sine theta, or equivalently, since this is a right angle triangle, I can also say that this is F square minus F square projection. These are both the same, they are equivalent to each other. And if I look at F is 100, sine theta is sine of 74, so this is going to be 100 times sine 74, or F perpendicular is going to be approximately 96 newtons. So I have F projection as 28 newtons, and then I have F perpendicular as 96 newtons. So these are just the magnitudes. We are not yet done, because we want to express these answers in terms of Cartesian unit vectors along their respective line of action. And so we take the following route for that. I have my triangle of interest. This is my triangle. This is a 90 degree triangle, though it may not look like one. This is F projection, this is the force F, and then this is F perpendicular. I know that the unit vector along this line was UAO, the unit vector along that particular line was UAC, and then the unit vector along that particular line was U perpendicular. Alright, so the first thing is, I already have the force vector F written in terms of its Cartesian components, and this we had was F times UAO. We had all the details given to us before. So this was 0I minus 80J minus 60K, so many newtons. Now F projection can be written as its magnitude times the unit vector along its line of action UAC. Magnitude was 28, and UAC was 0I minus 4J plus 3K divided by 5, which means that F projection was the following. After doing all these simplifications, this is going to be 0I minus 22.4J and 16.3K, so many newtons. And this is the force vector F. Now how do I find F perpendicular? I have the triangle law of addition here. Force F is F perpendicular plus F projection. This is the triangle law of addition. This is material that we have looked at during the first lecture of this semester. So from this we can see that F perpendicular is nothing but the difference between F and F projection. So I can now say that F perpendicular is the difference between F and F projection. So this is going to be the difference between F, which is minus 80J minus 60K, minus F projection was minus 22.4J plus 16.3K. Sorry for sneaking those things in. I hope this is visible to everybody. And once you do the calculations, F perpendicular turns out to be equal to the following. This is going to be 0I minus 57.6J minus 76.8K, so many newtons. And we're going to summarize all these results before we move to the last step of this problem. Right, in summary, I have the following. I have first of all the triangle, F projection, F perpendicular, and the force F. This was 100 newtons. And then the angle here we found out to be approximately 74 degrees. F projection was 28 newtons, and F perpendicular we obtained this to be approximately 96 newtons. Then we wrote everything as Cartesian vectors. I have the force vector F was 0I minus 80J minus 60K, so many newtons. Then the projection, which was the magnitude times its unit vector from A to C. This was found out as 0I, 22.4J, 16.3K, so many newtons. And then F perpendicular, which was the difference between F and F projection, and this answer was found out as 0I minus 57.6J minus 76.8K, so many newtons. Alright, so these were the things that we needed to find out. And the last question is, how do I find U perpendicular? And the idea is fairly straightforward. I know that F perpendicular is magnitude times its unit vector, which means U perpendicular is the vector F perpendicular divided by its magnitude, and so U perpendicular is the vector which is 0I, 57.6J, 76.8K divided by the magnitude of F perpendicular was 96 newtons, and so U perpendicular, after doing the simplification, is 0I approximately minus 0.6J and approximately minus 0.8K. Unit vector does not have any dimensions, and this is quite valid from the fact that F perpendicular is measured in newtons, magnitude of F perpendicular is also in newtons, and so the unit cancels themselves off. Alright, and just to give a brief review of what the problem was asking us to do. So here was the original problem. I have the Cartesian coordinate frame in 3D. I have a pipe of some kind. I have a fairly better picture right here. So this was the first picture given to us. I see that there is this pipe CBA. This is an L-shaped pipe, and then I'm told that at the point C there is some kind of a support for this pipe, but that is not sufficient. So there is a cable running from point A to point O, and there is a tension along this particular cable. And what do we need to find? We need to find the projection of this force along a line joining the point C and the point A, and we also need to find a force that is perpendicular to that projection, and this is evident in the figure drawn here. So I need to find first of all the projection of this force F along that particular line, and I need to find the vector that is perpendicular to the projection vector and lying in the same plane as the projection vector. And what did we do? We went through the basics of writing out the coordinates. We drew the triangle here. We found out that each vector is nothing but its magnitude times its unit vector. We discerned the unit vectors along the directions of F projection and the force vector F. Then we made use of the fact that cos theta is the dot product of this unit vector and that unit vector, and we were able to find out theta. Once we found out theta, this was a right angle triangle. We could find out F projection, we could find out F perpendicular, and then we made use of the triangle law of addition by saying that force vector F is force vector F perpendicular plus force vector F projection. These are all vector quantities. When you do the triangle law of addition, they are not scalar quantities, and then we were able to find out the final results. force vector F as a Cartesian vector, F projection as a Cartesian vector after finding out the angle theta, F perpendicular as a Cartesian vector using the triangle law of addition, F minus F projection, this is the answer. And then we were also asked to find out the perpendicular unit vector, and this is nothing but the ratio of the perpendicular vector by its magnitude, and this is the final answer right there. Thank you very much.